Welcome back to Calculus 1. In this lecture, we're going to introduce a central topic to calculus, something called an antiderivative. All right, let's think back throughout the course, way back in the beginning. A question that we were focusing on was, given a function, finding a derivative. We spent a lot of time on that. There were a lot of differentiation rules. Our primary three differentiation rules being the product rule, quotient rule, and chain rule. And a little bit after we introduced those, we gave the physical interpretation of this question. Given the position or position function of an object, find the object's velocity or velocity function. How we're going to approach this topic of antiderivatives is basically switching this around, kind of reversing the question. And the first version is, instead of being given the function and asked to find the derivative, now we're going to be asked to go backwards. Given the derivative, find the function that corresponds to that. Now, the physical question stated down there, which is of more interest to, let's say, physics and possibly engineering, is given the velocity of an object, find the position of it. And that's going to get you on the path to kind of where Newton's second law ties into this. Don't be overwhelmed if you feel like you've never taken a physics course, but that might relate it to what you've done in a basic or introductory physics course already. We'll just be looking at the mathematical side of things. All right, now the way I like to approach antiderivatives is, if we think with mathematics, there's some basic operations. What I want you to think now for calculus, one basic operation which applies for functions is finding the derivative of a function. Now, you kind of see through mathematics, each operation has an inverse or opposite. Addition, its inverse is subtraction. Multiplication, its inverse is division. And if we try to define this mathematically for the operation of finding a derivative, well, as it turns out, there is an inverse or opposite, which is called uncreatively an antiderivative. So that'll be how we approach it. If you continue on through the calculus sequence into calculus 2, you'll kind of see other ways to find antiderivatives, building off what we cover in our course right now. Now, what I want to point out before we get into this is there is a problem with the inverse of multiplication. There's a problem with division. We can't divide by any number. There's problems when we divide by 0. So what I want you to think going through this, and I'm leaving this a little vague right now, for our new inverse operation, that of an antiderivative, there's some sort of problem, not quite like division by 0, but there's a conceptual problem that we encounter when defining or dealing with this inverse operation. We'll bring that up at a certain point. All right, at this point, let's get started with some basic examples, just building off the tools that we have. And let's go with a really simple question here. This one is deceptively simple. If our function is x squared, what is the derivative? That's no problem. It's 2x. We apply the power rule for derivatives, which basically says we bring the exponent 2 down and then subtract 1 from the exponent. Now, we are going to define some rules for antiderivatives. And just think, for a power of x, like x squared here, to find the derivative, we reduce the power by 1. All right, let's flip this around to the question we're now interested with. Let's say the derivative is x squared. What must have been the function, f of x? Now, you might be able to make some guesses. We're kind of mentioning that we're reversing finding derivatives. And for the power rule, if we reduce the exponent or power by 1, you might expect that we increase here our power by 1 to find an antiderivative for x squared. Now, as it turns out, we can do that. but there's not a, I'll say, a single answer. So let's kind of just move forward. We kind of think with the basic power rule for derivatives. We try to add 1 to that exponent. That seems kind of like a good first possible answer. If you differentiate x cubed, well, you get 3x squared. What we want is a function whose derivative is just x squared. So this kind of function is not correct. X cubed differentiates to 3x squared. We want a function that differentiates to x squared. So x cubed here is not the correct antiderivative. Well, how do we get rid of that factor of 3 there in that derivative statement? Well, we can cancel it if we include an extra factor of 1/3. And now, if we combine that with the power rule to think how this works, what we can say is a function that differentiates to x squared is 1/3 x cubed. What we now say is 1/3 x cubed is an antiderivative of x squared. Now, before we move on, just check. If you take 1/3 x cubed and differentiate it, you apply the power rule. The 1/3 is thought of as being a constant multiple. You bring the 3 down. 3 times 1/3 gives 1, and you're left with x squared. So this checks out. 1/3 x cubed does differentiate to what we're looking for here, a derivative of just x squared. Now notice the wording. It says 1/3 x cubed is an antiderivative. This is implying that there's more than one possible answer. This is the start of those conceptual problems we mentioned with inverse operations. Specifically here, there's a conceptual problem when trying to define antiderivatives. Now, could we think of another antiderivative for x squared, a technically different function that still has x squared as its derivative? Well, as it turns out, we can. Recall from our basic differentiation rules, the derivative of any constant is 0. So what we can do is take, let's say, this first antiderivative we found, 1/3 x cubed, that does differentiate to x squared. We can then add any constant, here, 1, to that to get another antiderivative. So a second antiderivative we can say is 1/3 x cubed plus 1. If you check right below there, that still differentiates to x squared, since the derivative of 1, the derivative of any constant, is 0. Now at this point, you might be able to think, are there other antiderivatives? Well, we just have to add any constant at the end there. We don't have to have plus 1. You could have 1/3 x cubed minus 5. That still differentiates to x squared. You could have 1/3 x cubed plus pi. Pi is a constant. And you can probably see the pattern here. You can pretty much add any number after 1/3 x cubed, and you will get another antiderivative. How many numbers are there? An infinite amount of them. So the conceptual problem here with antiderivatives, what we see is if there is at least one antiderivative, then the function technically has an infinite amount of antiderivatives. That's very different than the problem of finding a derivative given a function. There was only one sensible or possible function for its derivative. Now, reverse that. If a function has an antiderivative, then there's going to be an infinite amount of them. What we'll write is the basic antiderivative, here 1/3 x cubed, plus some constant. And the standard notation in calculus is to write that as plus c. All right, at this point, this is again, very basic example. We're going to use this to motivate some definitions and everything that follows. So let's get to our kind of technical definition for an antiderivative. This is coming at the tail end of Calculus 1. Calculus 1 deals with differential calculus. Antiderivatives really, at their foundation, say something about derivatives, basically reversing that. So we'll see that reflected, for instance, in this definition here for an antiderivative. All right, the definition says, as we say, a function, capital F, is called an antiderivative of little f on an interval if capital F prime equals little f. So basically what this says is one function is an antiderivative of another if it satisfies a certain statement about derivatives. Now the notation is changing a little bit from what we were just using in the previous example. So let's revisit our basic or introductory example just to kind of make sense of this notation. Where we left off, we were mentioning about the plus c part having an antiderivative with plus a constant at the end. We're going to call this version with plus c the most general antiderivative, where we're going to interpret c as being some constant. All right, if we go back to our previous example, let's say our function is x squared. The notation's changing here. What we would look for is an antiderivative, a function, capital F, that differentiates to x squared. Still the same concepts, but the notation is different. So if our function, little f of x, is x squared, well, we did fine by basically reversing the power rule, a function that has x squared as its derivative. An antiderivative, we can write it as 1/3 x cubed and then plus c. So for our function, f of x, or little f of x, equals x squared, the antiderivative would be capital F of x equals 1/3 x cubed plus c. The lowercase and the uppercase denotions for the functions or names, that's kind of standard notation. Now, the nice thing about this definition is it basically gives us a built-in check anytime that we're calculating antiderivatives. What we can do is take our proposed antiderivative and basically just differentiate it. If we get the desired function, then we have the correct antiderivative. So pretty much every question that we cover here has a built-in check. We'll mention that when we get to some examples. And you can see here, our antiderivative 1/3 x cubed plus c does correctly differentiate to what we want, x squared. So we have a correct antiderivative. All right, now to transition to the next part before we get to some examples. This is a kind of an operation, it's the inverse of finding derivatives. And you might be kind of putting the pieces together and thinking, well, we had a lot of rules for finding derivatives. The primary ones, again, being the power, product, quotient, and chain rules. If we're saying antiderivatives reverse or are the opposite of derivatives, well, we might suspect that these existing differentiation rules could be reversed to give rules for finding antiderivatives. So a question we might be thinking, are there rules for finding antiderivatives? The answer is yes. There's a two-part answer. In our course right now, we'll be looking at some basic antidifferentiation rules. In your Calculus 2 course, you'll be looking at the more complicated ones, dealing with reversing the product and chain rules. But we'll save that for your Calc 2 course. All right, so let's proceed kind of expecting with our known differentiation rules, we're going to reverse those to get known or now new anti-differentiation rules. So as long as you have a good foundation on all of your previous differentiation rules, some of the following things that we get to should be familiar. We're just kind of flipping things around. All right, so we're going to give a list here of what I'll call basic antiderivatives. I'm calling them basic because they're going to come by reversing known differentiation rules. What I'm saying is if you know a list of derivatives, switch the columns around, and you basically get a list now of antiderivatives. So let's take a look at a few examples for how this works. Anything on the right side in the antiderivative column, you can check that is a correct antiderivative by differentiating it and see if you get what's right on the left of that. All right, so let's take a look at our introductory or basic example at the start of this lecture. We said, let's say we have the function x squared. What is an antiderivative? And aside from the plus c, an antiderivative is 1/3 x cubed. Instead of decreasing the power by 1 for finding derivatives, we increase the power by 1. All right, let's take a look at some other examples, still powers of x. Give yourself a few seconds and see if you can maybe hypothesize or propose what these functions' antiderivatives should be. So the functions being x cubed, and then separately x to the 4th. We'll check in a few seconds. All right, this probably shouldn't seem too complicated. You might be able to see some patterns forming here. For antiderivatives, it seems as if we basically add 1 to the power. So the function x cubed, its antiderivative should contain x to the 4th. Now, in order to get the precise matching for the definition of an antiderivative, we want to be able to differentiate our antiderivative and get the function. We would need kind of a factor, a fraction, to cancel out the exponent 4 coming down. So what we have for our antiderivative of x cubed is 1/4 times x to the 4th. Or you could write that as x to the 4th over 4 if you prefer. For the antiderivative of x to the 4th, we added 1 to the exponent to get x to the 5th, but to get the derivative to match up, we have that factor of 1/5. All right, now check those, differentiate what's on the right side, and you should get individually x cubed and x to the 4th, performing your check for antiderivatives. Now what these examples highlight are antiderivatives for powers of x. Recall there was a power rule for finding derivatives. We're on the verge of stating a power rule for antiderivatives. Now, before we move on to that, I'll give you a chance to write it down. What seems to be happening is we add 1 to the power or exponent of our function, and then we divide by the new power. So notice we have in our antiderivative of x cubed an x to the 4th, but 1/4. In the antiderivative of x to the 4th, we have x to the 5th, but with a 1/5 power in front. Now, at this point, with these few examples, you might be able to propose what this kind of antiderivative should be for, let's say, the power of x here, x to the n. See if you can maybe propose what the antiderivative should be. We'll check in a few seconds. All right, well, mentioning the examples above, it seems like we should add 1 to the exponent. So if our function has x to the n, our antiderivative should contain x to the n plus 1. And then we should probably divide by the new power, because we've been doing that in the previous 2 examples. So it seems as if we get this. Our function's exponent is n. The antiderivative contains x to the n plus 1. We then take that new exponent, n plus 1, and we divide by it. So we get our antiderivative here, 1/n plus 1 times x to the n plus 1. And that seems right, right? There is a problem. What is stated right there is actually incorrect. I don't want to tell you why. Pause the video and give yourself a little bit of time to think what might go wrong with this proposed anti-differentiation rule. All right, did you find it? Again, as stated, what's on the screen here is incorrect. Notice that factor in front, 1 over n plus 1, there's something in the denominator. There is a problem when you divide by 0. What value of n makes this expression undefined? Well, if n equals -1. Now, to make this precisely correct, we basically had a correct rule. The only exception is it doesn't apply, since we would get division by 0 when the value of n is -1. So what we have here is a precise and correct statement for the power rule of antiderivatives. The antiderivative of x to the n is 1 over n plus 1 times x to the n plus 1, provided or if n is not -1. The exponent could be any other value. It could be a positive exponent, could be a negative exponent, provided it's not -1. The exponent could be 0, could be a fraction, as long as the exponent value is not -1 for your function. This antiderivative rule that we call now the power rule applies. All right, well, what do we do if the exponent is -1? So what is an antiderivative for the function x to the -1? Pause the video and give yourself a little bit of time to think about that, and we'll check in. All right, did you get any ideas for what the antiderivative should be? Well, notice if you rewrite that expression, x to the -1 as 1 divided by x, using your basic exponent rules, now you might be able to think, do I know a function that differentiates to 1 over x? And you all do, because you're all experts in everything we've covered in the course so far. And you all recall that the derivative of natural log of x is 1 over x. So we reverse that around to now say an antiderivative for 1 over x is natural log of x. The absolute value is there for some technicalities. All right, since we're bringing up in our table here, logarithms, natural log, what goes along with logarithms are exponential functions. Now this one shouldn't be too bad. Do you know a function that will differentiate to e to the x? You probably do. Itself, e to the x. So e to the x is both its own derivative and antiderivative. And that is a remarkably interesting fact. Some of you may not be going on deeper into higher level science and engineering courses or mathematics, but this fact that e to the x, there's a function that is its own derivative and antiderivative, has some consequences for the way our universe actually looks. If you get to the point of seeing some of the rules for, I'll say basically like quantum physics and stuff like that, this fact comes back. All right, let's take a look at some other examples, other anti-differentiation rules that we already know. Let's incorporate some trig functions, every calculus student's favorite types of functions. Let's start with some simple ones here. See if you can propose what the antiderivatives of cosine of x and sine of x should be. Think about what functions would differentiate to them. Reverse your differentiation rules. Take anything on the antiderivative column, differentiate it, and see if you get those functions, cosine of x and sine of x. We'll check in a few seconds. All right, now the antiderivative for cosine should be straightforward. What function differentiates to cosine? Sine of x. The antiderivative for sine of x, however, is not cosine of x. Why? Check. Differentiate cosine of x. The derivative of cosine of x is negative sine of x. So we're off by a kind of a -1 factor. Well, we can fix that by putting an extra factor of -1 in front of cosine here. Now we have a correct antiderivative. Notice if you differentiate negative cosine of x, you get an extra negative, which cancels that -1 factor we put there, and you do get your derivative as sine of x. The positive and negative signs kind of work themselves out there. Okay, so there are some basic trig antiderivatives for sine and cosine. To really test your knowledge of how well you understand your basic differentiation rules, let me give you an attempt here at the following 4 functions and their antiderivatives. So see if you can find the antiderivatives for these 4 functions: secant squared of x, secant x times tangent x, 1 divided by 1 plus x squared, and 1 divided by the square root of 1 minus x squared. At some point, you all knew the answers in some form. See if you can recall and reverse your differentiation rules. All right, welcome back. Hopefully you were successful. Hopefully you still remember your list of basic derivatives. Do you know a function that differentiates to secant squared? You probably do. The derivative of tangent is secant squared. We now reverse that and say an antiderivative for secant squared is tangent. Similarly, we reverse our differentiation rules. Recall the derivative of secant x is secant x tangent x. We now reverse that to get this statement: an antiderivative for secant x tangent x is just secant x. All right, and what seems to be rather simple here, it's actually very important as you move on through calculus 2, the derivative of inverse tangent, we define that as 1 divided by 1 plus x squared. Because we know that derivative rule, we can reverse it now and say an antiderivative for 1 divided by 1 plus x squared must be inverse tangent of x. And similarly down there, for 1 divided by the square root of 1 minus x squared, its antiderivative is inverse sine, because the derivative of inverse sine of x is that expression there, 1 divided by the square root of 1 minus x squared. Now, hopefully you see kind of how all this fits together with our known differentiation rules. Right now, we're reversing them, giving us a rather large list of antiderivatives. There are others not on here, but they all come from your known differentiation rules. All right, at this point, we're basically going to jump to some examples, but to kind of prepare you for some of those examples, let's just kind of review some rules from what we covered already in this lecture, and then thinking back to some other rules for finding derivatives. All right, so let's first review here kind of what we introduced so far as some basic rules for antiderivatives. All right, the first and primary one that we introduced a few moments ago was what we called the power rule, but now the power rule for antiderivatives, which basically says is if our function is a power of x, x to the n, then our antiderivative is 1 over n plus 1 times x to the n plus 1. And again, that only works if the exponent, the power of n, is not -1. All right, thinking back to some other basic differentiation rules that were introduced when we covered the power rule for derivatives, we had what we call the constant multiple rule and the sum and difference rule. We don't even usually think of applying those. Basically, it's just what we used when we have constants multiplying functions, and if we add or subtract several different functions together, we have already incorporated using those rules in finding derivatives without even usually mentioning it. Well, from the way those differentiation rules work, we now get a constant multiple rule and a sum and difference rule for antiderivatives. It basically says the same thing. Constant multiples, well, we can just have it multiply now our function's antiderivative. And if we have, let's say, a function that's a sum or difference of two other functions, we just find an antiderivative for each part and then add or subtract their respective antiderivatives. Now, let's also think back to some tips we mentioned for finding derivatives. And a very useful tip that we mentioned in a lot of examples back when we were covering differentiation rules was you might want to rewrite your function before finding a derivative. Since that was such a useful tip earlier, it still applies now. Our new useful tip is to try to rewrite before finding an antiderivative. We'll see that in action in some examples in what follows. The last thing I want to cover in this first part of this lecture, we didn't include it in the table, at least not directly. What is the antiderivative of a constant function? So let's say, for instance, here your function f of x is 2. What is an antiderivative for that? In other words, what function differentiates to just 2? Think about it for a few seconds. And it should be 2x. Take the derivative of 2x, it comes out to be 2. We now have a correct antiderivative. Now, the reason we didn't mention this in the table is because we kind of already did, but we didn't mention it. You can think of the function 2 as a power of x. It's the case where the power of x is 0. Recall, anything to the 0 power is 1. So what we can do is express our function, little f, as 2 times a power of x, x to the 0. That's algebraically correct. And then we can apply the power rule for antiderivatives. The power rule does apply for antiderivatives if the exponent is 0. And if you do that here, notice you get your antiderivative of 2x, take your current power, which is 0, add 1 to it, which is 1, divide by that new exponent, so divide by 1, and now multiply the 2 there with our constant multiple rule. And if you simplify that, it all comes out to 2x. So constant functions really are a special case of the power rule for antiderivatives, where the power is 0. We're going to look at a few examples in what follows in part 2, which we'll pick up right after this.